Hello everyone, this is Dr. Lennon, and we're going to look at logarithmic equations today. So, remember, inverse properties of logs and exponential functions are kind of what allow us to solve equations, the main tools. So let's look at the inverse properties again, or recall what they are. And the inverse properties basically say that if I take the log base b of something with an exponential base b to the x, this is exactly x, and that's for any x. And if we do b raised to the log base b of x, this is also equal to x, but this is only for x greater than 0 because that is the domain of the logarithm. So x is first being plugged into the domain in property 2, whereas in the first one, you're doing b to the x, which is always going to be a positive value. So it's not going to cause any problem for taking the log of b to the x. So again, we have the special cases. Usually the ones that pertain to us are, we have the common log and also the natural log, because those are the two buttons that are on most calculators. So the common log would just be, okay, the log of 10 to the x is equal to x, and 2, if you did 10 to the log of x, this would be equal to x for x greater than 0. And then you would also have the properties if you use the natural log, so the base of the natural log would be e to the x, or the base would be e. So if you do the natural log of e to the x, this is equal to x, and e raised to the natural log of x is equal to x for x greater than 0. Okay, logarithmic exponential equations were ones where you had the unknown in the variable in the exponent of some expression. So a logarithmic equation means basically we have the unknown as the argument of an equation. So let's look at just maybe one of the most basic examples. So let's go ahead and say solve for x. We'll do a bunch of these. So part A, let's say we have the log of 5x minus 15 equals 2. Okay, so what we want to use when we're solving a logarithmic equation, so notice the 5x is inside the parentheses of the logarithm, we want to use property number 2 to cancel out the logs. So basically we want to make both sides the exponent of 10. So the equation is preserved so long as whatever you do to one side of the equation is done to the other. So on the left-hand side, we get cancellation from property 2, so we get 5x minus 15. And on the right-hand side, we can just simplify that to 100. So to solve the equation, we can add 15. And then we end up with 5x equals 115. And then we can divide by 5. And we get our answer. X is equal to 23. Okay, so let's have a look at another. Let's say we have, let's go ahead and do, a similar one with the natural log. Let's say the natural log of 3x plus 1 equals negative 1. So for this one, we have to make both sides the exponent of e. So here we would end up with 3x plus 1 is equal to e to the negative 1, or 1 over e. So then we would subtract 1 from both sides, so 3x is equal to 1 over e minus 1. And then we could divide by 3. So we would have x is equal to, so you're basically dividing each expression by 3, so 1 over 3e minus 1/3. And if you wanted, you could get a decimal representation for that. So let's see what that is. So that comes out to negative 0.21 if you round to 2 decimal places. But again, those are the basic examples for logarithmic equations. Basically, you can get rid of them by exponentiating with the base that matches the base of the logarithm, and then it just turns into an algebra problem. So these can get a little more interesting. So potentially we could have, more than a single log in play, and we may have to use some other properties of logs. So let's just recall our other log properties in case we have to use them. So there are 3. And again, they work so long as the bases match. So 1, we have log base b of m plus log base b of n. This will equal the log base b of mn. 2, if you have the log base b of m minus the log base b of n, this is going to be the log base b of m over n. And 3, if you have the log base b of m to some power p, this is going to be p times the log base b of m. Okay, so if we continue with the previous example, and just calling this next one c, we can see how some of these properties come into play. So let's say we have the log of x plus the log of 2, and let's say this is equal to 3. Well, we'd like to use the inverse properties to get rid of the logs, but we cannot do that straight away because there's 2 separate logs. So what we want to do is combine them using property 1. So log of x plus log of 2 is the log of x times 2, or the log of 2x. This will equal 3. So now we can use our inverse property and say, okay, well, 10 to the log of 2x is equal to 10 to the third. So we have 2x equals 1,000. And then when we divide by 2, we get our answer of 500. So x is equal to 500. D, let's say, so when we have something like this can easily turn into perhaps a quadratic equation. So how might that occur? Let's see. Let's say we have the log of x plus the log of x minus 3, and let's say that's equal to 1. Well, we can multiply the 2 expressions, putting the logs together, x times x minus 3, and this will equal 1 still. So expanding inside the parentheses, we have x squared minus 3x equals 1. And now to get rid of the logs, we can exponentiate both sides with base 10. So we have x squared minus 3x equals 10. And so this is a quadratic equation. So we want to subtract 10 from both sides. So we have x squared minus 3x minus 10 equals 0. So then this translates to x minus 5 times x plus 2. So we have 2 solutions here, x equals positive 5 or x equals negative 2. Now the thing about that is when we have these type of situations, we really want to check them to be sure that they make sense in the original equation, because remember, the domain of the original log is only positive numbers. So if you look at log of x plus log of x minus 3, if you plug in negative 2, you end up with the log of negative 2 plus the log of negative 5 equals 1, and the domain of the log is only positive values. So this is not a real solution. This is an extraneous solution. So our only actual solution to this problem is x equals 5. So you have to be careful when you have these things that turn into something like a quadratic equation. You might have some solutions that don't actually make sense in the original problem. So let's go ahead and maybe do a couple more and then look at some word problems. So let's say let's say we're looking at maybe we'll do one with log base 2. Let's say log base 2 of x is equal to 4 minus the log base 2 of x minus 6. Now it's the same deal. We want to get the logs on the same side so that we can put them together. So our first order of business is adding log base 2 of x minus 6 to put all the logarithmic expressions on the left-hand side of the equation. So now we have the log base 2 of x times x minus 6, and that will equal 4. So we have the log base 2 of x squared minus 6x, and that equals 4. And so now what we want to do, here we have a log base 2, so to use the appropriate inverse cancellation property, we need to make both sides the exponent of 2. So log base 2 of x squared minus 6x on the left, and we have 2 to the 4th power on the right. So the left-hand side we get cancellation, x squared minus 6x, and on the right-hand side we're going to get 16. So let's move that 16 to the left. So subtracting 16 on both sides leaves us with x squared minus 6x minus 16. Then we got a factor. So this factors as x minus 8 times x plus 2. So our two possible answers are x equals 8 or x equals minus 2. And we want to go ahead and see if either of those are extraneous. Well, we can already tell the negative solution is going to be extraneous because log base 2 of negative 2 would be undefined, and similarly negative 2 minus 6 would be negative 8, which is undefined. So again, this negative value is extraneous, so we do not use it. So our only solution to that problem is x equals 8. Okay, so let's look at maybe one more of that type. Let's look at one where maybe we even have to FOIL. So one last example. Let's say we have log base 2 again of x plus 4 plus the log base 2 of x minus 2, and let's say this is equal to 3. So again, we want to put these together. So we have the log base 2 using property 1 of x plus 4 times x minus 2, and this equals 3. So we want to FOIL on the left-hand side now inside the parentheses of the logarithm. So we get x squared plus 2x minus 8 by FOILing equals 3. And then we want to make both sides the exponent of 2. So we get 2 to the 3rd on the right. So now we're left with x squared plus 2x minus 8 equals 8. And we can subtract 8, and we get x squared plus 2x minus 16 equals 0. So I'm not sure, but I don't believe that factors. So if that's the case, we would have to use the quadratic formula on this one. Is that the case? Let's just retrace our steps. So plus 4x minus 2x is plus 2x in the middle. Yes. Yeah, so the only factors of 16 are going to be 1 and 16, 2 and 8, and 4 and 4. So none of those work. So we do have to use the quadratic formula or completing the square to solve this one. Either one doesn't matter. It's a simple one, so why don't we just use completing the square for practice. So x squared plus 2x equals 16, and then add half of 2 squared to both sides, so we get x squared plus 2x plus 1. 16 plus 1 is 17, so we get x plus 1 quantity squared equals 17. So x plus 1 is going to equal plus or minus the square root of 17, which means x is minus 1 plus or minus the square root of 17. Again, negative 1 minus the square root of 17 is going to be a negative value. So if you look at x minus 2, that's going to end up being a negative number, so that's going to be extraneous. If we look at square root of 17 minus 1, so why don't I write those down for you? I'll write down the approximations. So x equals negative 1 minus the square root of 17. This comes out to negative 5.12, whereas x equals negative 1 plus the square root of 17. That is going to come out to .12. So we need to make sure that when we plug that into the original equation, it doesn't turn out negative. So 3.12 will work, whereas negative 5.12 will turn out to be extraneous. So these ones end up being extraneous solutions. So extraneous. So our only actual solutions are negative 1 plus the square root of 17, which is about 3.12. Okay, so let's look at some application problems here. So application problems will often turn into exponential equations that we saw last time. So let's go ahead and look at a couple of those. So let's say example So suppose that the world population is growing at 1.2% per year. If we assume exponential growth, after how many years will the population double? So this is known as a doubling time style problem. So in general, an exponential equation will have the form, say, y equals a times b to the t, where b is equal to 1 plus r, and r is the percent growth or decay, depending on the problem. So since it's growth in this problem, we know that we can model our problem as y equals a times 1 plus 0.012. So that comes out to 0.012 to the t power. So if, so actually, and let's say a is the initial amount from looking at exponential functions. So basically, if we're looking at time to double, we just set y equal to 2a. So setting y equal to 2a and solving for t gives the doubling time. So it's a pretty easy equation to solve. Just divide on both sides by a. We know a is an initial amount, so it's some non-zero quantity, so division is okay. So that drops out, and then we just have the equation 2. It's 1.012 1.012. I was leaving that 1 out. Let me see if I can fit that in there. So 1.012. So we end up with 2 equals 1.012 raised to the t. Then we can take the log of both sides, whatever kind of log we want. And use property 3 to bring the t down. So we end up with t natural log of 1.012. And then divide by the natural log of 1.012. And that ends up being our answer. So we can put that in the calculator to get an approximate value. Again, you could have used common log if you are more comfortable with that, but as long as you're using the same log on both sides, you'll get the correct answer. So this comes out to about 58.11 years. And that would be your answer to this word problem. So that's known as a doubling time problem. We can also look at a half-life style problem. So what will a half-life problem look like? Well, you have something that's decaying instead. So in that example, let's say we have potassium 42, and it has a decay rate of 5.5% per hour. So meaning it, half of, or 5.5% of it every hour is decaying into something else. And how many hours will the initial quantity been halved? Let's try and figure that out. We're going to use the same model as last time. So we're going to use y equals a times b to the t. But in this case, now we have a decay rate. So r is going to equal negative 0.055. So that means b is going to equal 1 plus this negative 0.055. Which comes out to 0.945. So our model for this problem is y equals a times 0.945 to the t. So basically, to solve our problem now, we want to set y equal to 0.5 times our initial amount, 0.5a, and solve for t. So we get 0.5a equals a times 0.945 t, and we go ahead divide by a and solve for t. So we get 0.5 equals 0.945 t. Take the log of both sides. I always just take the natural log because it means I'm writing one less letter, so it saves a little bit of time, but if you like common log, you can use that one. So then we use the third property that allows us to bring the exponent down in front. So we get t times the natural log of 0.945. Then we divide by that number, natural log of 0.945. So we get our answer. T is this natural log of 0.5 divided by 0.945. And that comes out to 12.25. And remember, our time unit in this problem is hours. So we get 12.25 hours. So that would be our answer for this one. So those are the basic style of exponential type word problems you get. Perhaps we'll look at a few more But those are the main ones. Usually you'll have some type of exponential model, and if you have an exponential model, they're either going to tell you something about percent growth or percent decay, and you can use that to solve questions about how long it takes something to happen. So in some sense, you can think about any percentage can be translated to, if it's growth, a doubling time, or if it's decay, a half-life. So which is the problem we just did. If you ask how long it takes something to be halved, if it's a decaying quantity, that's also known as the half-life. So you can kind of use that terminology instead of percent change. It really just depends on how it's typically framed, which one to use. Anyhow, that's all for today. So this is Dr. London signing off.